and thank you for the invitation to speak here. It's really nice to see so many friends, and I hope to see you in person sometime soon if we finally can travel for conferences again. Okay, so today I will talk about penny-shaped fracture problem in the presence of a state monochrome surface elasticity. So to put this problem in a broader context, what I'm trying to do in this talk, and my iPad is a little slow for some reason, is I'm trying to model nanoscale structures within continuum approach. So due to progress of technology, nanostructures become very popular for various engineering solutions. And in this case, we talk about a typical length scale from 1 to roughly somewhere around several hundred nanometers and high surface to volume ratio. So that is one of the characteristic parts of nanostructures. So what the surface to volume ratio does is it creates a large number of atoms which experience different environment compared to the environment in the bulk. So in particular, atoms which belong to interfaces or boundaries have different neighbors and correspondingly rearrange when atomic structure rearranges to accommodate for these different neighbors. And correspondingly, we cannot model if surface area is very large, we cannot just ignore this rearrangement like we do for macro objects. So the completely honest approach to model this would be going from atomistic modeling. However, here the problem with atomistic modeling is a obviously large number of atoms, even for very small objects. So it's difficult computational to model from these structures atomistically. So continuum-based approach will allow us to take into account surface mechanics while at the same time being computationally efficient. So the main idea behind this approach is here we have a solid omega with some kind of surface sigma, and again when we use energy to model this object, we have this elastic energy functional which has two parts. So so this is our elastic energy functional, and here we have this part which is a standard bulk energy. So in this case, I talk about linear elasticity. So we have linear elastic energy here. And on top of that, we will add this part of energy functional, and that is surface energy. So in my talk, the surface energy has this form. So it depends on the surface strain tensor, I should say, I'm sorry about that, and on KS, which is a surface curvature tensor. So it depends on these two tensors. So when we deal with this functional, we can use calculus variations or use surface divergence theorem and modify this functional and reduce this functional to governing equations. And again, governing equations in bulk will be just standard standard linear elasticity equations in this case. And on the boundary, we have a boundary condition in this form. So here n is our exterior normal. Sigma would be the jump in stress tensor on the surface. Again, you can have on the interface, you can have jump in stresses. And exterior will be exterior part, external attraction applied to the surface. And this TS component is exactly the component that comes from that additional surface energy. So what is that surface energy component? Again, we can create various models by using different surface energies. So two most popular models currently are Gorton-Nordic surface elasticity models. So this is the older surface elasticity model. It's extremely popular for modeling nanostructures. There are thousands and thousands of research papers on this area, even in the last 5 years, just last 5 years. In this talk, I will, this area this model has been appeared first in 1975, and in this model, the surface is modeled as a thin elastic membrane which resists only to stretch but not to bend. In 1997, Stegman and Ogden pointed out one disadvantage of Gurtin-Nordic model. In particular, it cannot support compressive stress states on the boundary, and they suggested to modify this model by including resistance to bending. And this is the model I'm going to talk about today. So this area is intensely developing starting from 2016, 2017. So here are some references in this area. It grows on a daily basis. I probably should have updated it because in the last couple of months, probably were new papers showing up in this area. So, okay, so let's talk about boundary conditions. So boundary conditions, again, they are distinguished by presence of this additional component Ts, which comes from surface energy. So for Stegman-Ogden model, this component has this form. So nabla S here is a surface gradient. T here is a surface stress. So it was given by this formula. So U is a displacement vector. Epsilon S is a surface strain tensor given by this. So projection of surface of strain tensor onto surface essentially. Sigma 0, mu 0, and lambda 0 are the model parameters. So they essentially give the resistance of surface to stretch and other actions. Now, if we just take this condition, then that will give us Gurtin-Nordic model. So Stegman-Ogden model on top of that, Gurtin-Nordic component includes this. So M here is a couple stress tensor given in this way, and kappa and kappa S is a curvature tensor given by this formula. So it's kind of all looks complicated. It's all obtained from variational formulation by using surface divergence theorem and some tensor identities. Now, if we look at the aura of a model, we can see that if we just look at the Gurtin-Nordic model, so just this part, then that is a model of a second aura. So essentially it connects stresses to the second order derivatives of displacement. So in this sense, it's a second order model. Stegman-Ogden model is a model of higher order. So on top of, so this component, actually, if we look again at gradients here, that will be a fourth order model. So it adds on top of that fourth order curvature dependent component to our model. And in this particular case, in the case I present today, surface energy is given by this formula. So again, the first part here would be just Gurtin-Nordic surface energy, and this part curve is resistance to bend on the surface. Okay, so the simplest way to illustrate this model is for two-dimensional straight crack problem. So if you have just two-dimensional plane elasticity, then Gurtin-Nordic model will give you this boundary condition. So this would be an external traction on the boundary, and so this will be tractions, and this will be the component which comes from Gurtin-Nordic model. So you can see that tractions are connected to second order derivatives of displacements. For Stegman-Ogden model, again, we have all the same components which came from Gurtin-Nordic model, but then on top of everything, we will have this fourth order components. That's fourth order additional display component. Now you can see that Stegman-Ogden model depends on three coefficients, which again characterize resistance to stretch, resistance to bending, and something called pre-stress on the boundary on the surface of the object. So those are three parameters. Now, this is not the problem which I'm going to talk about today. I'm going to talk about a little bit newer results, and those results for axisymmetric problems. So for axisymmetric problems, we have a displacement vector here, which depends on which has just two components. So in polar coordinates, so we have UR and UZ and both depend on R and Z components, coordinates, and in cylindrical coordinates, and U theta is just 0. So this is a simplified three-dimensional model, essentially, again, reduces to 2 dimensions. So if we use this simplified displacement vector and we substitute everything back into our equations, then these are the boundary conditions which we get. Again, you can see that there are some second order differential operators here. There is a fourth order differential operator, which again comes from Zemlyanova model. Okay, so penny-shaped crack. So it is a crack shaped like a penny embedded in an infinite object, infinite solid. And again, we are looking for axisymmetric problem. So for this problem, the boundary conditions can be written in this form. So, and again, since this is a very symmetric problem, we can essentially, instead of considering the whole solid, we can consider just upper semispace. So, and for upper semispace, this will be the boundary conditions. So if you look at these boundary conditions, you can see that they are not homogeneous in a sense that we have different conditions outside of a penny-shaped crack compared to inside of a penny-shaped crack. So those are different types of conditions. So that makes this problem a little bit more difficult to treat. And I will talk about it more. Now, one other thing which I want to mention here are the tip conditions. So again, when you do your variational, you work with your operational formulation, you get essentially first you have a solid term which gives you your bulk equations. Then you get conditions on the boundary which will give you boundary conditions, and then you get also conditions on the boundary of a surface which will give you something which is called tip conditions. And these tip conditions in this case look like this. So those are just on the boundary of our penny-shaped crack, so just on the outside circle, essentially of this crack. We want to satisfy this, and tau, nu, and then here, so tau is a tangent and is a normal, and nu vector is corresponds to the vector which is perpendicular to tau, and so this triad of vectors. Okay, so for penny-shaped crack, due to the symmetry, two of those conditions actually disappear, and the only condition which is left is this one. So when we solve our problem, we also need to satisfy this condition just on the boundary of a crack. Okay, so how to solve this problem? Again, you can solve this problem using some of the classical methods which we have. So again, we have linear equations in the bulk. And it is known that these equations for axisymmetric problems can be solved by using two harmonic potentials, introduce two harmonic potentials, and for these two potentials, we can express all our stresses and displacements in the problem. So here are some formulas. So those are just the displacements and stresses I'm interested in. There are other formulas to express the rest of them. Now, since those are harmonic potentials, we can find those potentials, solve the equation, and obtain integral representation for our stresses and displacements. So here again, those integral representations. So here are A and B of lambda, two unknown functions. Those are the functions which we need to find using our boundary conditions. J0 is again a Bessel function of 0 order of the first kind. So now, if we would have classical problem, we would take these representations, substitute them in the boundary conditions, invert Hankel transforms, and that would reduce our problem to just, that would essentially solve our problem for A of lambda and B of lambda. Now, in our case, since again, the boundary conditions are inhomogeneous, they're different inside and outside, so we cannot do that right away. So we need to go a little bit around to work with this. So, and the way to do this, to work with this, is we can introduce an auxiliary problem. So this auxiliary problem looks like this. So I denote my derivative of displacement UCR inside of my penny-shaped crack of radius A by this G of R. So G of R is not something I know right away. It's just a function which denotes this derivative of displacements. And the same thing for this tangential stress, sigma ZR inside of a crack. I denote it's some kind of function H of R. And now if I look at this auxiliary problem, that problem has the same conditions inside and outside of my plane-shaped crack. So that is immediately treatable by these integral representations. So I can take my integral representations, substitute them in these boundary conditions, invert Hankel transforms, and that allows me to immediately find A and B. And A and B here are expressed through this G and H, which are defined again only inside of plane-shaped crack. So this allows me essentially to get rid of outside part of my surface and just deal with the part which is inside of a plane-shaped crack. Now, of course, for my problem, I don't know G and H right away. So that is something I still need to find. So now to find these functions, I take these representations and substitute them into my boundary conditions only inside, now only on the inside of a crack. Outside part is satisfied automatically at this point, since these conditions are the same as for my plane-shaped crack problem. So I satisfied outside conditions, and I just need to deal with inside conditions. So I substitute these representations inside these boundary conditions, and after some manipulation, I arrive at the system of two single integer differential equations for these functions G and H. So here G and H were rescaled. So again, in this theory, when we talk about sizes, A is typically at nanoscale. So we talk about 10 to 100 nanometers. So again, we don't want to work with that, and we want to rescale this at 0 to 1, so we can kind of avoid this nanoscale right away. So G and A, capital G and capital H are both rescaled values. P here is the normal stress applied on the boundary of the surface. So that is what causes the material to deform, essentially, creates deformation in the material. And we obtain these two conditions. So if you look at these conditions, there are some things which we can notice. So here the kernel TK1 is given explicitly by this formulation. So K of K and D of K here are complete elliptical integrals corresponding for first and second kind. And you can see what we have is R squared minus T squared. So that gives us, after some manipulation, that gives us singular kernel, singular integral over here. Now, this second equation, so first equation is essentially singular integer differential equation, since we also have this derivative up to third order of unknown. And a second equation actually involves derivative of K1. So strictly speaking, that is a hypersingular equation. It has the derivative of singular kernel. Okay, so this is the type of equations which we have. And again, another thing which you can notice here, this equation depends on three parameters. So we have gamma 2 over A, gamma 3 over A cubed, and gamma 1 over A. So those parameters exactly correspond to nanoscale. So if you look at the real values for which were computed for different materials, we can see that when those the scale goes to nanoscale, so A is again 10 to 100 nanometers. These parameters are relatively big, so you can see that this it has influence on your material. Surface has influence on your material behavior. If you go to macro scale, these parameters become so tiny that you just don't see influence of surface. In this theory works for nanoscales. Okay, so how do we solve this problem? We use regularization. So again, this equation suggests on interval 0 to 1, which is convenient to regularize. So first equation can be just integrated. So this integral operator or differential operators here can be inverted, and assuming that we're actually dealing with Stegmann-Ogden model, so this coefficient is not zero, we can integrate and we can obtain this equation. And this equation at that point is not a single equation, it's just a Fredholm equation, so it has a regular kernel in it. When we integrate this equation, we actually fix two constants, two conditions. So one of those conditions is tip condition, which ends up being fixed. Again, we have further order differential operator, integrate 3 times. So 3 constants, one of those constants allows to satisfy tip condition. Another condition constant ends up being fixed because of something which you really want to be satisfied. Otherwise, you get very not regular solution. So if you want any kind of regularity, you have to put another constant, fix another constant. And then we get one additional constant over here. So, so this is first equation. Second equation, so that is again hypersingular equation. And again, if you look at some papers in this theory, actually there are lots of papers which still just stick with hypersingular equations. I don't like dealing with hypersingular equations, so I prefer to convert them to integrated differential equation. And again, the way you do this is essential integration by part over here. And you integrate by part, you end up with some boundary conditions which need to be fixed. In particular, this value at value of this function at 1 should be equal to 0. So that is something which we need to fix later on, and we can do it. So there's no problem over there. So we end up with this equation. So now K3 here is a singular integral kernel. So it's of similar type as K1, just essentially variables changed, the order of variables is changed over there. And then this equation with respect to this function. So again, this equation can be regularized essentially by inverting Cauchy type integral. And the inverted allowing singularities of order 1/2 at the endpoints. And then we integrate additional, since we have derivative here. So that gives us 2 constants, and we do these parameters. And again, one of those constants allows us exactly to fix that this is equal to 1, equal to 0 at t equals to 1. So that condition ends up being satisfied. And then we have one additional real constant over there. So at this point, we end up with 2 real equation, 2 Fredholm type of equations with 2 additional real constants. And this is just a continuation of regularization. So again, another typical thing which you do in this type of problems is do symmetry from 0 to 1 to -1, 1, and that makes your equation nicer. So, okay. So how do we want to fix these constants? So, so let's look at numerical scheme. So numerically, I want to solve these equations, and the numerical scheme is based on Fourier-Bessel series. So we expand our unknowns, so in this case, I take them as these antiderivatives into Fourier-Bessel series. So J0 and U0k here is a k of 0 of a Bessel function J0. And AK, BK, and C0 are unknown constants. This part here comes from the necessity to fix certain behavior of a function J0 at t equals to 1. And that is kind of numerical issue. So if you want nice convergence, you kind of need to fix that behavior in a certain way. So again, I mentioned that I have 2 real constants. I know that I have 2 real constants, additional real constants. So the way I will deal with numerics is I will take these equations and I will substitute them into my singular integrated differential system of equations. And I will essentially cut the series at certain number m. And since I have 2 additional constants, it turns out that I will cut this series at n+2 terms and this series at n terms. so to allow for those two constants. And additionally, this zero constant here is present here because in numerical scheme, I do not fix the tip condition. So numerical scheme is made in such a way that I have to fix a tip condition additionally. Okay, so if I substitute this representations into my single integrated differential equations, use properties of Bessel functions, in particular orthogonality property of Bessel functions, but that allows me to come up with this relatively simple looking system of equations to find my coefficients a, k, and bk. And on top of that, I have two additional conditions. So this condition is essentially a tip condition, which I mentioned I need to fix additionally in numerical scheme. And these two conditions allow me to fix, obtain bounded fields at the crack tip. So that is kind of difference with theory, with a classical theory. In classical theory, at the crack tips, you have singularities of order 1/2, and you stresses and derivatives of displacements. So that is very classic. In this theory, you can actually obtain bounded fields in some cases. So in this case, again, those two additional constants which come from integration allow me to obtain bounded fields. So, okay, and this converges rather nicely. So the condition numbers generally around 10 cubed, 10 to the 5th, and they don't grow much with them. So some comparisons with classical conditions. So again, solid line here is a classical condition. Other lines are my solutions for various ends, and you can see that there is nice convergence to classical conditions, classical solutions. Another noticeable thing in this theory is that there is dependence, there is size dependence in this problem. So that's another deviation from classical theory. In for classical linear elasticity, you do not have size dependence. Once you introduce surface energy, you get size dependence in your problem. So in particular, here we have graphs for various gamma free. So gamma free essentially given by these values. And you can see that as your gamma free, which is impedance resistance, increases, your stresses near the crack tip decrease. So material becomes stronger. And these are some graphs for size dependence. So size dependence here are various radiuses of a crack, so 5, 10, and 20 nanometers. And again, you can see the size dependence. So depending on what A is, you get different stresses and different displacements. So that is kind of very interesting outcome of this modeling theory. Okay, so I'm almost out of time, so let me skip this. Let me just go to conclusions. So again, some of the outcomes of modeling with surface energy is we get size dependency on the solutions, which is a non-classical effect. We obtain smoother behavior over solutions near crack tips. So that is true for all kinds of problems solved with this type of modeling approch. Typically, again, solutions with surface energy behave smoother than classical solutions which you obtain. Gutenberg energy is noticeable at 1 to 100 nanometers. So that's kind of the application range for Gutenberg theory. Steigman-Ogden theory is more noticeable at smaller scales, so 1 to 10 maybe. So outside of that, it's very close. The solutions are very close to Gutenberg theory. And there are lots of future work which can be done in these areas. In particular, computations of surface parameters are difficult in this area. So since it's surface tension essentially in metals at nanoscale, so it's difficult to measure this thing. Usually it's done by atomistic simulations. Currently, there is a big interest in multi-physics models, so electromagnetic elasticity, so this type of models, and there are some results exist in this area already, but those are more difficult problems. And of course, there is a lot of different types of problems. So outside of straight and circular geometry, essentially, there are almost no publications in this area. Okay, so I'll stop here. Thank you very much. And any questions?
Thank you. Thank you very much, Anna.